Hello, welcome. My name is Jonas Karlsson. I work here at Google, and this is very happy to introduce Professor Withdrawal Litvin here, who's going to talk about the scalable distributed data structure here. This is a very interesting area of research. I was working with Withdrawal on some of the data structures for my thesis, and this is still an area which needs to be applied, but I think we're going to see more and more of it being applied. It's currently getting attention in P2P networks a lot. Professor Litvin is currently at computer science in University Paris Dauphine, and he is part of he's director of CERIA, and his research concerns is multi-database systems, data structures, and some of you may know the linear hashing data structure, which was invented by Withdrawal in the 80s, and is currently being used by almost all database systems for internal representation. You have Netscape browser, servers, Microsoft, Postgres, Sybase, SQL Server, etc. are using this data structure. So Withdrawal has been has a past here in California. He used to teach here at Berkeley, and also been at Stanford for 2 years. And he's been recorded many times, so he enjoys being recorded here again. And this is going to be a public talk, so any Google-specific questions, please take it after the talk, and we will be available here also. Thank you.
Okay, so I hope you can hear me with this mic. That works. Thanks. I would like to thank Jonas for the invitation, and I'm pretty happy to be at your place. I passed a number of times in front with the car, but never went into this particular building. So I hope you will enjoy the talk enough to justify the invitation. Now, I don't know how much time we have. 45 minutes with questions. Okay. So what I will present you, as you could see, read in the meantime, will be the new data structure, which is called the Scalable Distributed Data Structure. I will tell you in a moment what is it for those who are not familiar. And it belongs to the family called LH star, which means essentially distributed linear hashing. Now, I will talk a little bit more about it in a few minutes. According to these plans, first of all, I will overview for you the concept of scalable distributed data structures, as you might not be familiar with that, although it was invented here nearby in '92 at HP Labs when I was there by that time. We'll talk a little bit about P2P, for those who are not familiar with this concept. And then we will enter specifically this algorithm that has nice properties of being in some sense optimal, the fastest one from the addressing point of view. And we will also overview so-called churn management, which is essentially the high availability, which is absolutely very important in P2P environment, as peers can be quite often unavailable or leave the configuration. And then we will conclude. And now, I don't know the local custom. You want rather folks interrupt me with question, or you fire them up? Or?
It's up to you. We could leave a space in the end for questions. If people ask questions, please repeat them for the video recording. And then
OK, so you are free to ask the question on the way if you feel that something is not easy to understand. Now, the objective of this particular data structure is to adapt the SDDS methodology, which was not specifically designed for P2P. The concept of P2P did not exist by that time, to the P2P environment using some properties of the peers, which will appear in a few minutes. And as a result, this data structure, as far as I know, is the fastest one from the addressing point of view, because in case you miss the address, which is essentially that one peer incorrectly addresses the query to the peer which the original peer thinks should be the addressee, but the peer is wrong, then the forwarding of this message towards the correct address takes only one message, to compare with OAuth log messages, for instance, by CORD. So this property makes it the fastest structure at this time. in P2P environment, and probably the fastest structure ever, because there is no way to do better than one forwarding message in case of addressing error. And also, we have added the high availability to it, because in the P2P environment, if you don't have high availability, then forget about the scheme because of the churn. So that's whole goal. And the target is obviously very large scalable files, because this is intended to work on hundreds or thousands or millions of interconnected computers and intended for data that may scale all the time. And you will not see that data got somehow reorganized. So a little overview of what SDDS was. I do not intend to read all the slides. Well, you can read them. But essentially, a scalable distributed data structure is intended as a new, or was intended as a new class of data structures, where first of all, every data item was identified by an object identifier or the key. The characteristic property was that there was no centralized addressing, because it becomes a hotspot that is totally against the ideas in distributed computing. Now, originally, in such a structure, you could have servers that contained the data, and you have clients that had faced the application. And the servers usually were assumed to hold data in so-called buckets or pages, if you like. And the structure, any SDDS, evolved through splits of overloaded servers. So if you had too many records on a server, the server is supposed to split, and the new server is allocated to the address space, and some of the overflowing records and some other move to the new server. Now, the very important axiom is that the servers do not notify the clients about the split, at least synchronously, because this would, again, be very tough. If you have millions of clients, a split would be a very cumbersome process. Besides, the clients may be on and off. It may be your laptop, and then if you close the laptop, there is no way to notify that something changed on the servers. So how do the addressing proceeds in this case if you don't have centralized addressing and clients are not notified? Well, it proceeds through what is called client images. It depends then on the particular SDDS that you use, how the client image is structured. But essentially, the client image gives some image of the file state. And the client uses this image. And sometimes it's OK. Sometimes it's not OK because some server split and the client was not aware or merged if the data collection decreased. And as a result, the client can make the addressing errors, in which there has to be some system built in the servers which are able then to forward the message among them until it reaches the correct server. Now, how the client knows that something was wrong with the addressing process, it gets back so-called image adjustment messages that are sent by the correct server that finally got the query, and the message says something like, hey, your image was incorrect. Now we corrected at least partially what I know as on my data as the correction for you, maybe not the global correction. But at least in this correction, the data are sufficient to avoid that the client makes the same error twice. That's the axiom in every SDDS. So these principles were fixed in somewhere around 93. We have published a SIGMOD paper by that time with Marianne Neymat and Donovan Schneider, who are both in the Bay Area. Marianne Neymat, in the meantime, became vice president of Oracle recently, so pretty skilled lady. And after all, there is about 50 or more, well, maybe around 100 of SDD schemes around. If you want to see some of them, the best thing you go to some indexing scheme available on the web, which is called Google, and you ask for scalable distributed data structure or scalable distributed data structures in plural. You get something like 20,000 estimated reference count, and then you can look into, and you have dozens and dozens of papers presenting this or that SDDS. So It's pretty widely known now. Now, if we want to make some guidelines to that, people reconstructed somehow the classical data structures in the scope of the scalable distributed data structure axiom. So we have hashed-based scalable distributed data structure, and we have tree-based scalable distributed data structures. Part of the thing I have here does not seem to be visible. It's probably my fault. It seems that some color of the font does not go through. So it's unfortunate that I cannot correct it now. There are more than that. But anyway, something happened. No, it's on my computer is the same thing. So there is some bigger trouble. I will correct it on the copy I will leave with. So anyway, the tree-based structures are like, let's say, B-tree, but scalable distributed. It's called RP star, and other schemes called Baton by Jagadish and some others. Or they can be multidimensional, including a scalable distributed version of R-trees, if you are familiar with, which we have just presented at ICD in Istanbul, and many others. On the hash side, the basic structure is LH star, which was published in '93, linear hashing, distributed linear hashing. And there are many structures which are based on so-called distributed hash table. In fact, it's DHT. I don't know what is DDH. It should be DHT, which was originally proposed by Bob Devine in '94, and somehow took later by Hellerstein, who is professor at Berkeley, and Stoica, to the pretty well-known P2P structure, which is in fact an SDDS called Chord, where they use extensively distributed hash tables. And there are other schemes which we'll not look at. And finally, there are some schemes which introduce into the scheme the notion of K availability, which is essentially high availability. And we'll talk a little bit about, because the algorithm that I will show you today is based on that one, which was published in Todd's, ACM Todd's 2 years ago. And there is also a concept of some kind of security through the related concept called algebraic signatures. I will not talk about it today, but there was ICD 2004 paper on that, and there is the VLDB 07 paper on that coming. So if you are interested by this aspect of security, we can talk after the talk, but I don't enter it today, no time. So that's about the picture of typology of SDDS as by today. Here are the missing stuff. Here is the missing stuff. Now, there is another universe called structured P2P schemes, which are in fact SDDSs, and these are other SDDSs which are pretty well known today. Again, I will not talk about it. Now, go a little bit faster. How does an SDDS behave? Essentially, you have the clients or peers, like here, and then when the clients insert the records into the SDDS, then SDDS start to grow through splits and grows and grows and grows, and so on. Now, how the image of the client is managed? In this example, we have 3 clients. This client has an image that the file contains only one side or one bucket. This one thinks that the file contains 2 buckets. This one thinks that the file contains 4 buckets. But in fact, the file contains 4 buckets or 4 nodes, if you prefer. Not 4, I'm sorry, 7. But none of this client knows it, because maybe the clients didn't use this file when the last splits occurred, and the clients are not notified. So in this example, this client sends a query. It happens that the data the client was looking for are in this particular bucket. So the result comes back to the client, and the client is not notified that something was wrong with the image. Okay? In this example, this client sends the query, and it sends to the bucket number 1. This one is 0, this one is 1, because this client knows only about 2 buckets, so it cannot send it anywhere else. Now, it happens in the example that this query was not for this bucket. In the meantime, this data migrated through splits somewhere, so those SDDS servers have a built-in mechanism to forward, and finally, the correct bucket happens to be this one. So this bucket will send the image adjustment message to this client, and as a result, the client will adjust the image and we'll end up with the image of 6 buckets. You may notice that the 7th bucket is not in the image still. And the next time this client will send the query to this data item, it will send it directly to bucket 6. And as long as this item did not migrate because this bucket did not split, it will get the data item directly. Okay? So that's the principle of image adjustment messages in the nutshell. Now, there is a prototype of all those features, which is available at our site that you can download. Turns out that this prototype implements something that Jonas made as his thesis and published an EDBT paper, which is a pretty good achievement, called LH LH, which is a fancy way of combining the use of hash function for internode addressing with the hash function used for intranode addressing, which is not a trivial problem at all. And his thesis and the design of the algorithm was efficient enough to be still used, despite that it was done when 90s, beginning of the 90s something. So this is very efficient work, and we were very happy, and EDBT reviewers as well, because it went there. Now, this prototype works in distributed RAM. As you know, this is probably the future. If you looked on the, let's say, Jim Gray's last talks before his disappearance, he's claiming that the disk is becoming the archival storage. Everything will be in distributed RAM, so this system is quite advanced, and so on. So, well, just a little comment when we talk about 300 times faster, what does it mean in practice? In practice, it means that if you have a database, the response time to your query goes down from, let's say, 5 hours to 1 minute. That's what means 300 times faster search time. Okay, so it's very important, I think. Now, the other area that we had was the so-called P2P. It appeared in '95, as many of you know, through kind of idea of stealing essentially DVDs, movies and songs. But pretty quickly, people came into the concept that this is a useful concept, but they have to use something which is called structured P2P to avoid the flooding. Flooding is the query that you don't know where to send, so you send it everywhere. So once they started to do P2P, structured P2P, in fact, it became SDDS. Yes, sir?
Freenet never used flooding.
Yeah, that's well, yes and no. They used small world graphs at one point. But if you didn't know where it was on smaller scale, I would say the small world graphs were quite similar to flooding, at least if you didn't know exactly. That was my opinion after reading the paper. But still, you're right. Small world graphs, after a while, avoid flooding somehow, which is a pretty nice idea. Okay. So apparently, you are aware of this part of computer science methodology. So with respect to structured P2P, probably the best known work is CORD and also P-trees, which are by Karl Aberer, somehow a little bit less known, but predated CORD. As the typical performance with respect to forwarding is O of log of n, where n is a number of nodes. So if you have let's say, 1 million of nodes, then your query may need something on average like 20 forwarding. While LH star, I didn't mention it, has the upper bound of 2 messages only for various reasons. Now, LH star, I will not go very deeply into it. If you want to recall the features of that algorithm, there was a paper in TODS, in ACM TODS in '96, which describes it very much in detail. So either you go to ACM Digital Library, or I can somehow send you after the talk. So now we go specifically to the new algorithm. Now this algorithm is based itself on a variant of LH star, which was designed for high availability and published in TODS 2 years ago, called LH RS, RS standing for Reed Salomon, It was the kind of the codes that we use to manage the high availability, parity. And it has P2P because we wanted to merge the idea of SDDSs and P2P. What was this idea? What was the merging point? In SDDS methodology, we had client and servers, and the client were not, let's say, reliable at all, in the sense that the client could be your laptop, and the client could be on and off completely. In the P2P terminology, as we understand it, the clients are not, such clients are not very well seen, especially because to be on and off and just use the file as in SDDS, they are called free riders, for instance, in Freenet. Rather, everybody who wants to be a peer makes some commitment that it will share also the burden of having the data. So here we assume that every LH RS node has the client component and the server component. This is a kind of the commitment. Now, this changes completely the nature, because if this node becomes also a server component, it means that it offers some kind of minimal reliability, because it's not fair to have a server component and hold some data and frequently to be offline. So under this assumption, the internal design of the algorithm somehow changes, in the sense that we can organize some kind of passage of information between client component and server component that I will show shortly. And this passage of information between the client and server makes the system more efficient than otherwise if we have, let's say, traditional clients and servers. Now, so in this architecture, we have some peers. Each of them has a client component, has a server component, so holds some data. But we also have, or may have in the system, some nodes which would like to be the peers, but simply there is no way for them yet to have data, because there is not enough data. We call them the candidate peers. So somehow, like you say, I want to join the community, give me some data whenever you have this data, and then we will not forbid you from working, because there is no data for you. So then you act as a spare. You are just waiting for data till you get this data. In the meantime, you are allowed to use your client part as a free rider, because you are not the free rider, because you committed to have data whenever the file needs you. And those guys are called candidate peers. And they are managed somehow, as I will show in a moment, by some peers. And from the point of view of those peers, they are called pupils. And at least some of those peers may have pupils. Not necessarily they have, but they may have. And for those pupils, those guys are called tutors in the vocabulary, you will see. And essentially, the tutors make aware of the pupils, which are only a few, about the file evolution, as you will see very shortly. Now, pupils have to be somehow identified to the tutors, and the identification we use is simply the IP of the pupil, which becomes kind of the hash key. That's the same thing as in Cord, for instance. Okay. Now, this essentially on what you see on the left side, it makes reference to the internal structure of LH star file. It's essentially, on the server part, we have a parameter called G, or J? Yeah, J, which is so-called level of the hash function used for the server. And here we have the client image, which is essentially defined by two parameters called I prime and N prime. It will become clear in a moment what is it. So now I have to recall a little bit of annoying stuff about LH star. There is a little bit of formalism, but not too much, not to overload the talk. So essentially, if you take an LH star file, so also LH star RS file and many other versions of LH star, each record has some global position in the file, which is defined by the linear hash functions, which are somehow listed here. And essentially, if you want to know where the record should be, then you take the key of the record, you apply the current hash function defined by what is called file state with the value I. It gives you the bucket number, which is 0, 1, 2, 3, 4, 5, and so on. And the record is supposed to be there in this bucket. except that what happens that nobody knows those functions. Essentially, nobody knows the value of I and this parameter n, because the clients, because there is no centralized addressing component. In fact, there is one which is called coordinator, but this component is only used for split, and no client has access to that. So the client has to compute the address otherwise, and they have the image, which is essentially using the same functions, except that every client uses the value which is called I prime and n prime in this image, which are simply the best approximation the client know of the actual values of I and n, which are unknown to the client, okay, to any client. So each client has some value of I prime and n prime. It defines the addressing schema. Each client uses the same function, which are essentially hashing by division. It has very nice properties. And, but each client knows only its local values, okay? So then knowing that, you have to know a little bit how the file expands. So the file expands to splits. And the splits in linear hashing have the particularity, which made this algorithm well known. That is when you can have the overflows on some buckets, but if you have an overflow on the bucket, it doesn't mean that this bucket will split immediately because of the overflow. The overflows, the splits are managed using something which is called the split pointer, and that's the value of this variable n. And this value of the variable n points to the next bucket to split. And the coordinator somehow manages, I will show you in a second, what is the next bucket to split when some bucket has an overflow. So the scheme is roughly as follows. If a bucket overflows, it alerts the coordinator saying, well, I have an overflow. Then the coordinator will say to some other buckets to split. Okay, and this bucket will split, and then, which surprises always. And then things seem not OK, because this bucket, the original bucket still stays with the overflow. But in fact, the movement of the pointer is organized so that sometimes later, this bucket that had an overflow will split in turn. So the splits are somehow lazy a little bit later. There are some theoretical properties behind that motivated this scheme, obviously. Okay, so you have some details of the scheme, and this is organized so altogether that the addressing space expands gradually. And every time a split occurs, there is a new address added, which is always the number equal to the number of addresses in the file plus 1. That's a property of the division function. That's why it is used. There are two hash functions with those nice properties. One is called division, which is well known. And the other is called multiplication function, which is a little bit less known. I don't know why, because it's a really beautiful function and described in details in Knut's The Art of Computer Programming book. But somehow people do not read The Art of Computer Programming. Maybe it's too old, and somehow nobody uses the multiplication function. It has the same property. Anyway, so you see the bottom line is that when the file, you start your LH star file, you start with this bucket called 0, and then the first split will add the bucket 1. And then the pointer comes back to 0, and the next split uses the next linear hash function, which will, with I greater by 1. So the next split will be from 0 to 2. And the bucket 1 will split into the new bucket 3. And then the pointer comes back to 0. And then in the next overflow, 0 will split to 4, and 1 will split to 5, and 2 will split to 6, and 3 will split to 7. And now the file has, as you can see, the load of the file is distributed over 4 buckets. And then the pointer comes back to 0, and we start to use the higher level of I. So now the first bucket will split to 8 using I equals 3. And the bucket 1 will split to 9, and 2 will split to 10, and so on, till we get to the 15. And then it comes back to 0, and we start to use the next linear hash function, and so on and so on. See? And every time the new split adds the bucket which is just behind the existing ones. So it's a smooth extension, and every split distributes loads evenly on the bucket that splits and the new bucket. So the file is never really overloaded. There are a bunch of papers on the web accessible through Google that analyze the load factor of LH star. If you like mathematics, people made very nice things to guess what could be the overall load in the buckets under the schema. But bottom line is at about 70% of load factor. Now, what is the real new things in LH star RSP2P with respect to LH star RS? One of the new things is that since now we have the peers and the server communicates with the client on the same side or has some tuples, then in the moment when the server splits, it can adjust the client's image. What didn't exist in any previous version, so it does it immediately using this algorithm, which is pretty trivial. It simply says, OK, I just split, so I know perfectly what is the level of me, my bucket, what is the hash function used, and I know perfectly what is the next bucket to split, which will be the next one behind me. So A plus 1, if this is the bucket to split. So I pass you on this information. Now, at this particular moment, you as my favorite client, because you are on my node, you are just my client component, you perfectly know what is the state of the file, what is the value of I and N. So those values are equal. So you set up your I prime and N prime to I and N, and that I know. And at this particular moment, you are very lucky because you will know the exact state of the whole file. And that's exactly what happens. It's a big benefit. Okay, so then the things go obviously in different way, which is that the client progressively become desynchronized with the file state, the actual file state, because other buckets will split and they don't inform this particular client. But at the next round, when the pointer comes back to the same bucket, the client will be synchronized again. And it happens for every client component on every peer, see? And it also happens to the people. So how does it work? For instance, in this example, this bucket splits. These are just values that you can study after the talk. Sends a message to the coordinator saying, well, I have an overflow. The coordinator happens to be pointing the bucket P1 for splitting. So it sends a message to P1 saying, now you split. P1 does the split. And P1 does the split and adjust the parameters of this client component through this message. And the file expands by one bucket, and the P1 sends some data to the new bucket, which is P3. And after the split, coordinator adjusts, I'm sorry, it was a little bit too fast, adjusts its image to A equal 2 and N equal 0. Of course, you have to believe those values, but you can study the talk after the slides after the talk and convince that those are true. Now, the other part is now imagine that the server gets an incorrectly addressed query because the client didn't know that some split occurs. How the server know where to forward? It turns out that the server will know where to forward simply executing this small algorithm here, which is essentially saying, OK, I got this request, so I check with my level of the hash function I know whether this key falls down to me after executing this linear hash function hj. If it falls down to me, then the client didn't make an error. If it doesn't fall down to me, so it means that in the meantime, I probably split, but the client is not aware, so I will need to forward where I have created a bucket. And it turns out that can be only one bucket for that, so the second line of this algorithm will tell where exactly this particular peer is supposed to forward the key, which was incorrectly addressed to him. And there can be only one such address. And when it comes to on the other side to that peer, which is there is a child of the one that split, on the other side, it will be for sure the good address, as we will show in a minute. Okay? So the first line is checking that it is the correct address on the peer, on the server part of the peer. And the second line is forwarding it in case the address was incorrect. And that's the whole algorithm. As you can see, it's not really complicated. How do we adjust the image? It's again the pretty simple algorithm, which says somehow, hey, I got the incorrect address. So I am bucket A, I exist. So now take a note of this, and the take a note of this formally translates to this algorithm. And again, you can somehow look afterwards. Simply the client will adjust the images, saying, oh, if this guy exists, so my I prime and N prime have to be at least so-and-so, and the so-and-so is defined by those 2 lines. Okay, exactly 3 lines, let's say, 3 instructions. Okay, so you will see it after the talk. So in an example, just in a nutshell, imagine that this peer wants to insert the key or search for the key where the value of the key is 9. So it turns out when it calculates the address of 9 with respect to its components, it will be somehow 9 modulo 2 power 2, which gives the reminder of 1. So it sends it to the bucket 1, thinking that this is the good address. The bucket 1 checked with respect to j equal 4, but j equal 4 is the division by 2 power 4, which is 16. And obviously, when you divide remainder of 9 divided by 16, it's not 1, but it's 9. So it will say, hey, it's not for me. So where it could be, but it would be to the bucket. It has to be forwarded to the bucket that I have created when I moved from j equal 3 to j equal 4. And this can be only the bucket which is number 9. So the address that I just calculated, this is the second line of the forwarding algorithm. So it will resend it to the 9, and 9 obviously have to accept this because there is no other possibility here. And you can check it manually. So this will be the end of the process. Okay? And finally, the bucket 9 will send the IAM to P4, and P4 will adjust its parameters to those saying, hey, I know now that 9 exists, so here it's how it works. Okay? So this is a little example of file expansion. So again, we have to go a little bit faster. So in this case, there is an overflow, and then what I show here. This guy will split, so it sends the message about the new parameters it will have to its pupil. That's a basic purpose of the slide, and the pupil will essentially know what is the file state and will remain in sync with the peer that split. Okay, so that's what will happen to the pupil, and by the same mechanism, the same algorithm, pupil will know less or more what is the file state, less or more, but enough to be in sync. So what is it all about? What is the result, the final result? The final result can be stated in those 3 theorems, which is essentially that under this scheme, the maximal number of forwarding messages for the key search is exactly 1. This is the worst case. The other operation I didn't spoke about, which is called scan, when you send a query to various, it's a non-key query, so you send it to possibly to all the nodes because you don't know where to send it. It's a kind of flooding. Under this assumption, it turns out that the maximal number of rounds for a scan search is 2, which is, again, the best results. And finally, the third theorem will say that under the axioms of structured P2P and SDDS, most likely there will never be any algorithm which will be faster in that sense than the one that you have just seen. So it has an optimality problem. Now, there is the proof of this in the talk, but I will skip it because we don't have enough time. Essentially, there are a few slides you see that show what could happen to the file from the perspective of the bucket that tries to address something. So for instance, here we have the bucket A, and this part is the image that this bucket A has of the file. In fact, the image has evolved because the pointer N moved to the right. There were some splits, and those splits have evolved the image here and have evolved the image here. Okay? So now what can happen when this bucket, this peer wants to address something? So if the addressing of this peer falls down into the peer which was not yet split, you see there cannot be forwarding. This is this part of the file. If it falls down because of the key value into the part that already evolved, that there was split, they can be a forwarding. Not necessarily there is one, but they can be. And then the forwarding concerns this part of the file that was unknown to the client, to this client component. And finally, there can be another situation. Everything was split, and the pointer went back to 0 and came back. And then again, as long as we are not in this part, they can be a forwarding. Okay? That's as simple as that. For the property 2, about the number of runs, is a little bit more complicated for the folks unfamiliar with the algorithm. So I just displayed, and if you really want to know the details, then I left an extended abstract of the paper on it with Jonas. You can look into the paper. Okay. So let's skip it. Okay. Let's come back to the last part in a few minutes, which is called the churn management. What is the churn? Churn, it means that you have those nodes, those peers who are on and off. They are there, and then they disappear for various reasons. How is it managed in this scheme? It is based on the TOTS paper scheme that I told you, called LH RS. In LH RS, in fact, all the peers are divided or grouped into something which is called reliability groups. And you see here, so some of those peers are reliability group, and each reliability group is provided with some parity buckets. In this example, you have 2 parity buckets per reliability group. And the size of the reliability group is fixed. For instance, in this example, we have every 4 buckets constitute the reliability group. So the bucket, for instance, 0, 1, 2, 3 will have two buckets added, which are called parity buckets. And the bucket 4, 5, 6, 7 would have also parity buckets, and so on and so on. Okay? Now, within the parity buckets, we have the parity, we have so-called record groups provided with some ranks. And these record groups, each record group, data record group that you can see here, have the parity records which are calculated here. Same in the case of the LH RSP2P, the same is applied to the tutoring records, which are essentially the records which say, I have the pupils or I don't have the pupils. And those tutoring records also have to be protected against churn, so they have their own parity records here. The big deal, of course, is how do we calculate the parity in this case. And the TOTS paper gives a scheme which, to my opinion, is the most efficient up to now, using a particular class we have invented with the co-author of that paper, who is professor here at Santa Clara, which is a particular class of Reed Salomon codes. So let me stop here. The nice property of this stuff is that the Reed Salomon codes, as we defined them, allows you to have as many parity records as you like here. And if you, in this example, if you have 2 parity records here, it means that you can lose any 2 of the data records here, and the parity calculus will reconstruct this bucket. Okay? You can lose up to any 2. If you want to have a better protection, then you can set up 3 parity records per reliability group. Then you will be protected against 3. Why it is so important? Because when the structure scales up, then the probability that you have multiple failures grow up as well. So we have the concept of so-called scalable availability in this system, where the number of parity buckets protecting your reliability group goes automatically up with the file size. It's an automatic process. So you have to see the paper. Now we have 2 things that we can have in a peer-to-peer system, whether the peer living with the notice or without notice. If it lives with the notice, then it somehow notifies the first one of the parity bucket, which is called the reliability group manager. And the reliability group manager will find a candidate peer. That's why they have all those pupils. And will somehow move the data from the living peer to the peer that leaves the configuration to the candidate peer, and the things are done. Okay? The more complicated case, when the peer lives without notice, and suddenly you don't have those data. Okay? Then the Reed Salomon parity calculus goes to the full swing, And well, basically, you have to look the paper to see how it works. It's a little bit like RAID, except that it uses not only XOR calculus, but also multiplication in Galois fields. And finally, it can recover what was lost with this peer. Why we use Reed Salomon? Because in a reliability group, it may of course happen that several peers leave without notice at the same time, and you have to be protected. So in this case, there will be simply the reconstruction. Basically, somebody will address this peer that is gone. So if it does not reply, then the query will be sent to any other member of the reliability group, the next peer. This one will alert the parity coordinator, reliability group coordinator, and this one will simply recover the peer on some candidate peers, and that's it. Okay. So, and the answer will come back from the new peer. I will show it from the new peer, and the client will notice that there is a new physical address of the bucket that responded. Okay? Now, the most difficult case is the following one, when there is a communication failure and the peer somehow failed and then recovered. But in the meantime, this peer was recovered somewhere else. So you wake up, you don't know that you were cut off of the rest of the community, and it may happen that some other peer also doesn't know that you are cut off and will send you a query, despite the fact that, in fact, you were reconstructed somewhere. So this is an annoying case, but not that annoying. In fact, whenever your query is an update, then the parity peer will know that something happened to the peer, which is gone, because the update requests have to necessarily be forwarded to the parity bucket just for update of the parity. The real problem is with the search, because the search is normally not forwarded to the parity bucket, and simply it can go to the peer which doesn't know that it was reconstructed somewhere, and you can get a fake response to your search, okay, without knowing that this is a fake response. So we have a new concept which we call the sure search, okay, which is that even if you really want to be sure that the result is always correct, then you set up the LH RSP2P file so that even the search is forwarded to the reliability group coordinator, and this guy will always know that the bucket, the peer that was gone because of the transit failure is really gone. So it will say, hey, you are not the right guy. So it will forward it to the right guy, which is somewhere there, and this guy will respond to the peer which asked the query, the search, and this peer will notice that it was wrong, adjust the image, and that's it. Okay? So this sure search concept is a new one. I've never seen it anywhere. It looks simple, but it's still new. So I guess in the nutshell, I told you everything about this algorithm. So what is it? It's a hash-based scheme which has a nice property of require only one forwarding in the worst case, and this is the unique property of this algorithm up to now. It also protects efficiently against churn, which is somehow a big problem with few answers up to now, as far as I know. If you want to see on the state of the art, you look into papers by Kubiatowicz, who works a lot on that at Berkeley, and they might get different ideas from what I presented you, at least appreciate the idea that I presented you. Kubiatowicz's schemes are very good, by the way. A famous paper about managing the chaos that I strongly encourage you to read if you're interested by the domain. And finally, it is intended to manage very large scalable files, obviously, because of the simplicity of the addressing and because of the lack of any tables. It is intended for peer-to-peer configuration going up to millions of nodes if you need them. And I guess should have numerous applications because of its nice properties. Whether there's any application at Google is an open subject, but apparently you work on something called big table, I understood. So naturally, it seems to be a big table. Now, current and future work, this algorithm is pretty recent, so we are trying to implement at this point based on work of some other guys, and do performance analysis and do nice variants, some of them being addressed already in the paper I leave with Johan. Okay? So that's it for me. I think I didn't run over time. Thank you for your attention, and open for other questions.
Thank you very much. So I think we have.
So almost.
Almost, yeah. So if there's any questions.
You talked a lot about how much time these queries take. You know, it takes one hop at most in the worst case. And I'm still a little confused about the space requirements. Are these minimal because it's a hashing-based algorithm, so you don't have to remember a lot of state, or is there a lot of state that the nodes have to remember?
I'm not sure I understood completely the question. You talk about storage space requirements?
Yeah.
Okay. The load factor of this target is the same one as for, about the same one as for LH star and any dynamic hash algorithm, which is about 70% or precisely log 2 of E for the data, application data. Here we also have a little overhead for the parity data, obviously. Now the overhead for the parity data depends essentially on the size of your reliability group. So if you take the size of reliability group, let's say 16, which seems to be quite practical, then, and you decide to have one parity bucket when the file is small for those 16 data buckets, then you will add on it 1/16 to the load factor. If you decide to have 2 buckets, parity buckets, you will have 2/16 and so on. Okay? So I'm not sure whether I responded completely, but that's about it. So it's pretty space efficient, as efficient for data as P3 dynamic hash schema of any kind, extendable hashing, and so on.
Linear hashing, or LH star, has one of the properties that the data which a client needs to keep about the structure is quite minimal, and it's only these 2 free variables which keeps the state. So
essentially, those are 2 state parameters plus IP addresses, of course, because if you send a query, you have to know where the peer is. That's obvious.
Any more questions? All right. Thank you very much for coming. And,
okay. Okay, thank you.